Welcome back to Teen Tutors. In today's video, we will be covering Unit 6 of AP Calculus AB, which is Integration and Accumulation of Change. In today's lecture, we will be covering determining integrals geometrically, Riemann sums, indefinite and definite integrals, as well as U-substitution and the first two fundamental theorem of calculus. Before you start the video, make sure to print out the guided lecture notes in the description so that you can follow along as I teach. Now, without further ado, let's get into the video. So let's begin our discussion on integrals and accumulation of change by talking about what actually is an integral. Well, in simple terms, if the derivative represents the slope, well then the integral is going to represent the area under a curve, okay? So basically, if we have a function, let's just make it look like this. I'm not even going to define it, right? Then the integral, let's just call this f of x, right? So the integral of f of x will then be the area under that curve. So you see in these questions, we have the integral from something to something. So basically this is saying from an x value of 0 to an x value of 2. So let's say we say the integral from the x value of 0 here to, let's say, the x value of 3, right? And let's just say that this is the x value of 3. Well, then that answer, and we should add a dx here, that's just proper notation. We should add that then this integral would be whatever the area under here is. So we first learn how to integrate these using geometry. So in this question, we're asked the integral from 0 to 2 of 2 dx, right? So if we draw the function 2, right, because this represents our function, what is the function of f of x equals 2? Well, that is just a straight line, right, at 2. And then we could say, okay, well, from x equals 0 to x equals 2, well, then what would be that area under that graph? Well, the area under the graph, this would just be a square. So you would say that the area just equals base times height, right? So it just equals 2 times 2, which is 4, right? So then the integral then from 0 to 2 of 2 dx would then equal 4, right? And so then we look at another example from 0 to 4 x of dx, right? How would we integrate that? Well, we could say, okay, well, what does this look like? Well, what is the graph of x, right, of f of x equals x? It's just like this. And from the value of x equals 0 to the value of x equals 4, well, what is our y value here? It's going to be 4 comma 4, because if x equals 4, then y equals 4. And so if we draw this, this is just going to be a triangle, right? So the area here would just be 1/2 base times height, right? So we can model that as 1/2, the base would be 4, and the height would also be 4. So you get 1/2 times 16, which is 8, right? So then how else can we estimate integrals using geometry? So you guys might think, okay, well, we can do that, but then what happens for a function like this, right? Where we cannot just draw it as a rectangle or draw it as a triangle. You'll also maybe see that you can draw it as a hemisphere, not a hemisphere, but a semicircle, and you could also draw it as a quarter circle. And that would be, for example, if you had the integral from, a to b of, let's say, the square root of 9 minus x squared. Well, you could look at this as the square root of 9 minus x squared is just this, right? So then you could get the area, right? But we're not going to do one of those examples. And so how could we actually estimate any type of integral using geometry? Well, the answer to that is going to be via Riemann sums, okay? So we are going to definitely have to know how to use Riemann sums for FRQs, okay? So this is going to be a very important concept, right? So let's take a look at what we can do here. Now, before we start talking about Riemann sums, a whopping 98% of viewers that watch this channel regularly are not subscribed. So make sure that if you find videos like this one helpful, you subscribe to the channel so you don't miss out on any future unit reviews or multiple choice and FRQ review sessions that we will be posting throughout the month to help you prepare for the AP exam. So how do we do Riemann sums? Well, what we basically do is we take a function, and what we're going to do is we're going to say, let's say we have this function, f of x, and we want to estimate it using a Riemann sum. We're either going to take left, right, or midpoint values, right? And then we are going to estimate the values over a total interval using that value. So what that actually means is, let's say we're going to take a left endpoint as we are for this first example. Well, let's say we're going to have a couple left endpoints. So let's say I'm going to take some intervals. So let's say we have this subinterval, and then we have this subinterval, and then this subinterval, and they should be about equal length, right? And so the left values of each of these intervals, let's say starting at the point 0, let's make into a rectangle. So here, our value for x equals 0 is just 0, so it would just be a straight line there, right? And let me put this into a different color, just be a straight line here, right? And then what about our left value for here? So what we're going to do is we're just going to make a rectangle, right? And so we're going to say that we're just going to call this whole area that area, right? And then finally, we could look at this last interval and we're just going to say it's here, right? So while this is not a great estimate, as we make the interval smaller and smaller, this will get closer to our actual integral, and we will talk about that when we get there, right? So here it says approximate the area under the curve from x equals 0 to x equals 6 using left endpoints and 3 subintervals. So here's how we do this. Well, if we have 3 subintervals and we're going from x equals 0 to x equals 6, right? How would we split this up? Well, to split this up into 3 subintervals, we would go from 0 to 2, and then we would go from 2 to 4, and then we would go from 4 to 6, right? That would split it up into equal subintervals, right? So what are the values we are actually going to pick? Well, if we're using left endpoints, we have to pick the left point, right? So what we're going to do is we're going to estimate this based on, okay, well, we're basically just going to add rectangles, okay? So the first rectangle would be base times height, right? So the base here is going to be 2 because that's the actual length of our subinterval. So we're going to have 2 times f of 0, right? Because that is going to be our left value. For example, here we had our left value of 0. Okay, so we're gonna call that f of 0, right? So plus we're going to have 2 times then f of 2, right? And then plus again 2 times f of 4, right? And so those are going to be our left subintervals. So I can make this into 2 times f of 0 plus f of 2 plus f of 4. And so if you then plug that into this function, right, you're going to get 2 times, you would have 1 plus 9 plus 33, right? So then if you add them all up, you're going to get 2 times 43, which is going to give you 86, right? So then what if we approximate it then using right endpoints, okay? So again, the intervals we actually have are 0 to 2, you know, and then we have 2 to 4, and then we're also going to have 4 to 6, right? But then instead of using f of 0, f of 2, and f of 4, we're going to use f of 2, f of 4, and f of 6 because that would be the right side. So if we take a look at this function, right, and that, by the way, is not 2x squared plus 1. This is just some arbitrary function, right? So if you then take a look at this function and we were going to use right subintervals, what would that look like? Well, again, I'm going to split this up into 3 equal quadrants, not quadrants, just 3 equal parts. And then the right side, those intervals would look something like this, okay? And then we could also have, you know, this last one, let's call starting here, right? And so that's going to be our right intervals, right? So again, you see, you know, this one has a little bit over, you know, this one's going to have a little over, this one's going to have a little under. But as we make the intervals smaller and smaller, our answer will get closer and closer, and we will eventually have an actual interval, right? So here we would have 2 times f of 2 plus 2 times f of 4 plus 2 times f of 6. And we can write this as 2 times f of 2 plus f of 4 plus f of 6. And again, our actual function is going to be, it was 2x squared plus 1, right? So we can then write this as 2 times, we would have 9 plus 33 plus 73. We're going to end up getting 2 times 115, which is going to equal 230. And so see how drastically different these two answers are. So another way we can do this is we can use a midpoint. Okay, so then when we use midpoints, it's going to be the same process, but instead we're going to use the middle, right? So if again we have these 3 subintervals, so we have 0 to 2, and then we have 0 or 2 to 4, right? And then we have 4 to 6, right? We're going to pick the middles, right? So we're going to have the middle of 0 to 2 is 1, the middle of 2 to 4 is going to be 3, and the middle of 4 to 6 is going to be 5. So what we're going to have is 2 times f of 1 plus 2 times f of 3 plus 2 times f of 5, right? So this would then be 2 times f of 1 plus f of 3 plus f of 5, right? So this would give us 2 times f of 1 plus f of 3 and then plus f of 5, right? So this would then give us 2 times 3 plus 19 plus 51. and then that would give us 146, right? So we actually don't know what the integral is from 0 to 6 yet, so we can just hope that our midpoint is closest, right? On the exam, what they're going to do is they're just going to ask you to approximate using the right, left, or midpoint. They might ask you if it's an overestimate or underestimate, but we will talk about whether or not it'll be an over or underestimate when we talk about our FRQs, right, in our FRQ practice videos, right? So let's now look at what goes on with the trapezoidal rule. So what is the trapezoidal rule? Well, what we can do is we can take the Riemann sum and turn it into a trapezoid. So how about when we have this f of x, right? Instead of just picking left or right points, right, if we have these two subintervals, or let's call it 3, right? And let's make this go like this, right? We can make it into a trapezoid. So what would that look like? Well, instead, and let me make this a different color, we can draw this like this, okay? And these are then trapezoids, right? And then those would be trapezoids that would be have these points at where the endpoints are, right? And then we could go here to here, right? And then that would also be a trapezoid, right? Okay, so how could we do this? Well, what is the area of a trapezoid, right? So that's going to be 1/2 base 1 plus base 2 over the height, right? So what this is actually going to look like is we're going to do 1/2 times we're going to have f of a plus f of b plus f of b, and that's going to be all over, it would be over the delta x, okay? So here we're asked to estimate the area under the curve y equals ln of x from x equals 1 to x equals 4 using a trapezoidal sum and delta x equals 1, right? So we're going to have our subintervals have delta x equals 1. So we're going to start at 1. So we're going to have 1 to 3, 1 to 2, 2 to 3, 3 to 4, right? So we're going to have 1/2 times for 1 to 2, right? It would be times f of 0, or f of 1, not f of 0, plus f of 2, and that would be over 1, right? Because delta x is 1. And then we would have plus 1/2 f of 2 plus f of 3, and that would be over 1 again. And then we would have plus 1/2 f of 3 plus f of 4, and that would be over again 1, right? So we can factor out a 1/2, and we're basically just going to have f of 1 plus 2 f of 2 plus 2 f of 3 plus f of 4, okay? That's just if you simplify this. So it would be 1/2 ln of 1 plus 2 ln of 2 plus, we would then have 2 ln of 3 plus ln of 4, right? We could write this as 1/2 times 0 plus ln of 2 squared, which is 4, plus ln of 3 squared, which is 9, plus ln of 4, right? We could then expand this or fix this by saying that this is 1/2. We could use our rules that ln of a plus ln of b equals ln of a times b, right? So we would do 16 times 19, which is going to be 144, right? So ln of 144. And then finally, we can simplify this once more by saying that a ln of b is going to equal ln of b to the a power. So we could write this as ln of 144 to the 1/2 power, which is ln of the square root of 144. So it would be ln of 12, right? So that would be our answer here. Okay, so let's now talk about actually defining the Riemann sum. So if we have an integral from a to b, and we're going to talk about how to solve this, that can equal the limit as n approaches infinity from I equals 0, the summation to n, of f of a plus b minus a over n times b minus a over n. So basically what you're going to do is you don't have to understand what this means. You are literally just going to have to match this up on a multiple choice with set this up. So convert this integral to this or vice versa. Okay, so you do not, again, you do not need to know how to actually solve this. Okay, they will not ask you to solve this. So for this question, we are asked to write this as a Riemann sum. So all we have to do is we are going to write this as the limit of n approaching infinity, right? And then we're going to have a summation from I equals 1 to n. and then it's going to be f of a plus b minus a over n times b minus a over n, right? So what it's going to be is, okay, so what is f of, what is this, right? So basically, you're going to take f of, so 3 minus, and then your x, instead of x now, what you're going to have is where you start. So here it's just 0, right? So that's not important, right? So we would just have a 0. And then for your x, you're going to have the b minus a. So how much did you change from 0 to 5? And that was 5, okay? And so you would have 5, and there should actually be an I here. So I should say there should be an I here, okay? I'll actually put this, I'll put this over here, okay? So you would then have 5i over n, and it doesn't really matter. Again, you just have to know this formula. You don't actually have to understand what it's talking about. And then squared, right, because this was an x squared. And then this would be times 5 over n. Sometimes this will go on the outside. It's the same thing, right? So then in the next question, we have the integral of x cubed dx, right? So we can write this as the limit as n approaches infinity, right, of, let's write the 3 over n on the outside, right? Why would it be 3 over n? Because the distance from 0 to 3 is 3, right? So 3 over n, that gets rid of this part, right? Times the summation from I equals 1 to n of what we would do is it would be f of 0, because that's our a, plus 3i over n, right? So let's actually write that out. So it would be the limit as n approaches infinity of 3 over n times the summation from I equals 1 to n of, we would then have just 3i over n cubed, right? Because we just have x cubed, so we're just going to do 3i over n cubed. So that's, it's pretty basic actually, and most of the time if you just understand this, you just know this formula, you can just match it up on the exam and you'll get the question right. You don't actually have to know how to solve this. Okay, so let's now talk about integrals, right? So an integral is known as an antiderivative. It is literally the opposite of a derivative. So for example, if we know that the derivative of 2x is equal to 2, then the integral of 2 is 2x. Now hold on there because that is technically not true. The general solution is denoted as the integral of f of x dx is equal to capital F of x plus c. So what does this c mean? Well, if we have the integral of 2x, right, or the derivative of 2x, right, that gives us 2. But so does the derivative of 2x plus 7, right, because this constant differentiates to 0, right, so we would also get 2. And so does 2x minus 109,532, right? The point is, we don't know what this is. So when we integrate, we have to add a plus c. If you integrate correctly on an FRQ and you don't put that plus c, your grader will take a point off. It is imperative that you put that plus c there. Okay, so what is then the derivative of 7x? Well, or the integral. So we should say, okay, well, what differentiates into 7, right? And that would be 7x, right? So it would just be 7x plus c, right? And so then what would be the integral of 8x? So here we know that if we have x to the 1, right, we used power rule. Okay, originally we had x squared. So then you say, okay, well, what did this number here have to be in order to get that, let's just say a, in order to get that a times 2, right, when we did power rule was 8, right? So you would then say, okay, well, then it's 4x squared. And then we have to add that plus c. So we look, okay, what about 5x to the 4th plus 3x squared minus 10x plus 3? Well, so the first thing you always do, especially with power rule, you're going to add 1 to the exponent, right? So it's x to the 5, and then you say, okay, well, what number has to go here so that when we use power rule, it'll multiply with that power to give us, you know, the 5, right? So the answer there is just 1. And then again, for the 3x squared, you make it x cubed and say, okay, what do we multiply 3 by to get the 3? And it's just 1, right? And then you would have minus, you would have an x squared, and then you have to multiply a 5 by that 2 to get 10, right? And then you would have plus 3x, and then plus c, right? You take a look at one more. We have 12x cubed plus 6x plus 11. So the first thing we do here, we're going to have x to the 4th, right? And then what multiplies with a, right? What do we have to multiply 4 by to get 12, right? The answer there is 3, right? So 3x to the 4th. Plus for the 6x, we're going to have an x squared. And we say, okay, what does this 2 need to multiply with to get 6? And the answer there is 3. And then just plus 11x plus c, right? So what about this one? 8 over x to the fourth. So when we are integrating and we are over x to a power, it is usually easier, unless it is some number just over x to the power of 1, to write this as the integral of 8x to the negative 4 dx. So what we would then do is we would say that we would still do the same thing. So we're going to add 1 to the exponent, so x to the negative 3, and then say, what does negative 3 have to multiply by to get 8? And the answer there is going to be negative 8 over 3, right? So we can write this as negative 8 over 3x cubed plus c, right? So let's now take a look at some more examples, right? These are going to be a little more challenging. So we have cosecant squared of x plus 1. So we recall that the derivative of cotangent is cosecant squared, right? And so we could just write this as negative cotangent, and I should have said the derivative of cotangent is negative cosecant squared. So we're going to have to write negative cotangent of x plus 1, right, plus c. Why? Because when we differentiate this, we're going to have to use the chain rule, but this x will end up differentiating into 1, right? So we would get positive cosecant squared of x plus 1 times 1, right? And that would give us our cosecant squared of x plus 1, right? Okay, so then again, we look at the 2x minus 7 dx, right? And so here's what we're going to do. So this can be written as 2x minus 7 to the 1/2, right? So we're going to have to do a little thinking, right? Because there's going to be chain rule if we are going to, once we integrate this, if we want to differentiate back to it, we're going to have to use chain rule, right? So let's think about this. Well, again, the first thing you are always going to do is you are going to add that 1 to the power, right? So we're going to have 2x minus 7 to the power of 3/2. And then we know that if we were to differentiate this, we're going to have a 2 on the outside. So what we're going to do to offset that is multiply it by 1/2. Okay, we're going to multiply it by 1/2 to offset the fact that we would have to multiply by 2 when we differentiate it using chain rule. And then finally you'll say, okay, well, what multiplies by 3/2? That would give us a 1 in front here. And so the answer there is 2/3, right? So your answer to this one, it looks like the 2's here would cancel. You're just going to get 1/3 times 2x minus 7 to the 3/2 plus c. Right, and so let's look at a couple more. We have 3 times x plus 1 cubed, right? So again, first thing you do is we're going to add 1 to this power. So it's going to be x plus 1 to the power of 4, right? And then you say, what does 4 multiply with to make this in front of 3? And the answer there is going to be 3 over 4, right? And we don't really have to worry about this being x plus 1. We could integrate it the same way as an x, because what's the derivative of x plus 1 when we do chain rule? It's just 1, right? So then we have to add that c. Now what about this? 1 over x plus 5. Well, recall that the derivative of u prime over u is going to equal, or actually I should say this is backwards, right? I should say the derivative of d, so d over dx of ln of u is going to equal u prime over u. So it looks like this is actually going to be ln, right? So all we're going to do is we're going to say, okay, so on the bottom we have x plus 5, and when we differentiated x plus 5, we just got 1, right? So this is going to just be ln of, we have to put absolute value here, x plus 5 plus cy, because ln cannot be negative, okay? So, or the inside cannot be negative, right? So when we look at one more where it's a little more confusing because we have chain rule, right? So what we're going to do is we're going to say, okay, the first thing we do is we need to add 1 to this exponent, so 7x plus 3 to the power of 6. Then you say, okay, what does this 6 multiply with to get the 12? And that's going to be 2. And then finally, you need to multiply by the reciprocal of 7 in order to offset that when we do chain rule, right? So you're going to get 2/7 times 7x plus 3 to the power of 6, and then plus c. Okay. So now what happens when these are a little more challenging? Okay, what happens when we can't just think about the chain rule in our heads and just do it easily like that? Well, we know based on chain rule that f of g of x, if we differentiate that, will be f prime g of x times g prime of x, right? And so we can say that if that is true, then the derivative of f of u is f prime of u prime. So this is basically a new way of just saying we're just going to change u for g, right? And so what we can do then is just follow these steps, okay? So what we can do is, if we notice that in the problem we are multiplying two different things, and if we differentiated one of these factors, we would get a multiple of the next factor or just that factor, we can do something called U-substitution. So here's what we do. We say that u is going to equal whatever the thing that we can differentiate is. So I look here, I say, okay, if I differentiate x cubed, I'm going to get 3x squared, right? So I can say that u is going to equal, we make it this whole term, not just the x cubed plus 7. Why? Because if I differentiate all of x cubed plus 7, I'm still only just going to get 3x squared. So you want to get rid of as much as you can. So we're going to say u equals x cubed plus 7, right? And then what you say next is you differentiate both sides. So the derivative of u is just du, okay? And that's going to equal 3x squared dx, okay? So look at that. This 3x squared dx gets rid of all this and just replaces it with u. And this u gets rid of all this and just replaces it with u. So what we would have is we would just have the integral of our u to the 4th du, okay? So what would be the integral of that then? Well, it would just be 1/5 u to the 5th, right? And then plus c. So now what we do is we substitute back our u. So it would be 1/5 times x cubed plus 7 to the power of 5 plus c. So this might be a little confusing, but let's take a look at another example, right? So we have 9x squared times the square root of 3x cubed plus 7. Look at this. If we differentiate this inside here, right, we will get 9x squared, right? Because the derivative of 3x cubed is 9x squared and the derivative of 7 is 0. Okay, so we're going to say that our u equals 3x cubed plus 7, and then our du equals 9x squared dx, which means that this is the integral of just the square root of u du, right? Because we get rid of all of this and make it du, and then this just becomes the square root of u, right? So then how do we integrate this? Well, I'm going to rewrite this as the integral of u to the 1/2, right? It's better to integrate with exponents and not roots, right? So we're going to have u to the 3/2, right? We have to add that 1 to the exponent always, and then we say, what do we have to multiply 3/2 by to make this 1? And the answer there is 2/3, right? And then obviously we have our plus c. So this becomes 2/3. We have to substitute back in our u. So 3x cubed plus 7 to the 3/2 and then plus c, right? So let's take a look at one more. We have 5x over 4 secant squared of x to the 5th minus 4. So this one's a little tricky because we actually have to identify what are we going to make our u, right? So if we can just get the integral of secant squared, we can find that, because what is the integral of secant squared of u? It's tangent of u. So let's say, okay, well, I can differentiate x to the 5th minus 4 into 5x to the 4th, right? So let's say that our u equals x to the 5th minus 4, and then our du would equal 5x to the 4th dx, right? So that's going to get rid of all of this, and this is just going to become u. So we're just going to have the integral of secant squared of u, right? And so what would that equal? That would just be tangent of u plus c, right? So this would give us tangent of x to the 5th minus 4 plus c, right? Pretty simple, right? Okay, so let's now take a look at another example here. We have 3 square root ln of x over x, right? So we realize that we can write this as the integral of 3 square root ln of x, right, times 1 over x dx. So look at this. If we differentiate ln of x, we are going to get 1 over x, right? So perfect. We found our u and our du. So u here is going to equal ln of x, and du is going to equal 1 over x dx. So this will just become du, and this will just become u. So we're going to have the integral of 3 root u du. We could rewrite this as the integral of 3 u to the 1/2, right? And then so how would we solve this? Well, the first thing we're going to do is we're going to add the 1 to the exponent and say, what do we have to multiply 3/2 by to get 3? And the answer there is going to be 6 over 3, so just 2, right? That'll get rid of that 2. And then so we'll do 2 times 3 over 2, which will just give us 3, right? So then plus c. So we're going to have 2 times, we then have to plug back in our u, so ln of x to the 3/2 plus c, or plus c, not x, right? So then we have sine of x over cosine of x. So what we want to do is we can't have du on the bottom. So the first thought might be, okay, let's differentiate sine of x and make our du cosine of x, right? But that's not going to work. We need our du on the top. So what if we just say that u equals cosine of x, right? And then we say, okay, du would then equal negative sine of x, but there's a problem, right? We don't have a negative sine of x dx here. So what we do is we then divide by, we could divide by -1 and say negative du equals sine of x dx. And then look at that. We've gotten rid of all this, and we're just going to have a negative and then a du. So what this would end up being is this now becomes our u. So we just have -1 over u du, right? So what would this be? Well, what's the integral of 1 over u? It's just ln of u, right? So it's going to be negative ln of u. Then we could have a plus c. The plus c can go on the outside because if we put it on the inside, we're going to have negative c. That's still just c, right? It's just some constant that we don't know. So we're going to have negative ln of cosine of x, right, plus c. Okay, so let's take a look at one more. We have tangent to the 9 of x times secant squared of x, right? So how about we need to get rid of the secant squared. Why? Because I know that I can differentiate tangent into secant. And if I make my u secant, I'm going to get what? The derivative of u is going to be secant of x, tangent of x dx. That's not really going to work. So we're going to say that our u equals tangent of x, and then our du equals secant squared of x dx. And look at that. That's going to get rid of all of this, right? So we've done a good job. And then this would just become u. So we're going to have the integral then of u to the 9 du. Right, so we would get u to the 10, and you say, what do we have to multiply 10 by to get just a 1 here? So that's going to be 1/10, and then plus c. So we're going to have 1 over 10 times tangent of x to the 10 plus c. Okay, so then what happens when it is not as simple and straightforward? So what we're going to have to do is we're going to have to here, for example, no matter what we make our u, it doesn't look like we're going to differentiate. So either way, if we make it x minus 4 or x plus 1, we're going to differentiate into 1 dx and run into an issue, right? Because this is not 1 dx and this is not 1 dx. So there's a big problem there. So let's just take a look at this, right? We know the biggest rule we cannot break is that we don't want du on the bottom. So let's make u equal to x minus 4. So then du would equal 1 dx. Okay, so now there's a problem, and the problem is that this doesn't get rid of the x plus 1. What we really need to do is just get rid of x, okay? We need to put it in terms of u. So we could say, okay, what is x in terms of u? So we would say u plus 4 equals x, right? So then we could say that this is the integral. Instead of x on the top, it would be u plus 4 and then plus 1. So we would have u plus 5 over the square root of u. I'm going to rewrite this as the integral of the square root of u plus 5 over the square root of u, du obviously. This should have a du as well, which is going to equal the integral from u to the 1/2 plus 5u to the negative 1/2, right? So then how do we integrate this? And again, this should have a du. So we would have u to the 3/2, right? And then we need to multiply that by 2/3 to get a 1. And then plus, we would have a u to the 1/2, and we have to multiply that by 10 to get 5, right? And then plus c. So then after that, we just plug in our number for u. So that's going to be x minus 4. So 2/3 times x minus 4 to the 3/2 plus 10 times x minus 4 to the 1/2, and then plus c, right? This should have a plus c. So u to the 3/2 plus 10 times x minus 4 to the 1/2, and then plus c, right? And this should say x minus 4. My apologies. Okay, so in this next one, we have an x plus 1 and then a 2 minus x. It doesn't really actually matter which one you're going to make into u here. It actually does. We should say that it's going to be this one because we don't want, we need to get rid of this to the 4th, right? If we differentiate this x plus 1, we're just going to get x, or we're just going to get 1 dx, and then what happens to this to the 4th? You always want to differentiate the one that has that power, okay? So we're going to say that our u equals 2 minus x, and therefore our du equals negative 1 dx. And so we run into the same problem here, that this is not going to get rid of our x plus 1. Right? So the first thing I'm going to do is I don't want a negative dx ever. So I'm going to then say that negative du equals dx. I can also then say negative u equals 2 minus x, right? So I can then say x equals 2 minus u. So I'm going to make this the negative integral, okay, of x plus 1 times u to the 4th, right? So then the problem is we can't have an x here. Okay, we need it to be u. Okay, so this is going to be negative times the integral from, instead of x, we're going to have 2 minus u. So it would be 2 minus u plus 1, so 3 minus u, right, times u to the 4th du. Okay, so we would then have negative integral of 3u to the 4th minus u to the 5th du. And then now we can actually integrate it. So we're going to have u to the, and this should be to the 4th. So we're going to have u to the 5th, and we're going to multiply this by negative 3/5, right? Why? Because there's a negative here, so I'm going to now distribute it. And then we're going to have a plus, we're going to have a u to the 6th, then it's going to be 1/6, so that we'll get a 1 in front, right? And then we'll have a plus c. So it'll be negative 3/5 times 2 minus x to the 5th, and then we will then have a plus 1/6 times 2 minus x to the 6th, and then plus c. Right, so let's now talk about the fundamental theorem of calculus. Okay, so before we get into this, we are going to have to evaluate integrals from actual a to b's, right? That's what we did on the first page of this lecture, right? So we can write this as if the integral of f of x dx equals capital F of x plus c, then the integral from a to b of f of x dx equals capital F of b minus f of a. So basically, we are going to differentiate our f of b or f of x, and then we're just going to plug in our top and bottom bound, and then we're going to subtract them, right? Some quick things. The integral from a to a, this should say a to a, of f of x dx is going to equal 0. Okay, this is because if we have no change in our x value, we can't have any change, we can't have any area under that graph, right? Additionally, the integral of f of x plus g of x dx, we can separate them into an integral of f of x plus an integral of g of x. Okay. Additionally, we have the integral from a to b of c times f of x dx equals c times the integral from a to b of f of x dx. So we can take this c outside, right, if we have a constant. Additionally, this is the fundamental theorem of calculus. Okay, this is the first fundamental theorem of calculus, is that if we have an integral from a to b plus an integral from b to c, that is just the integral from a to c. Basically what this means is, let's say I take an integral, right, from, let's say, here to here, and I want to add that then to an integral from here, which is the same point I'm trying to make, to here. That could just be seen as the integral from this point to this point. Okay, we don't have to stop in between. Additionally, the integral from a to b is negative integral from b to a, right? So if we want to change those bounds and switch the lower and upper bound, we can just make it a plus, right? So let's try to rewrite these as single integrals here, okay? So we have negative 4 to 3 f of x dx minus negative 4 to 7 f of x dx plus 3 to 8 f of x dx, right? So here's what we're going to do. We are going to write this as the integral from negative 4 to 3 plus, we're going to change the sign of this, the integral from negative 7 to 4, and then plus the integral from 3 to 8. So it looks like if we take these two integrals, that's going to just make it go from negative 4 to 8, right? So we're going to have the integral from negative 4 to 8. That's using that a to b and then b to c, right? So negative 4 to 8 plus the integral from negative 7 to 4. This should be a negative 4, right? So then look, this now means that we can rewrite this as the integral from negative 7 to 8, right? So our integral here would just be negative 7 to 8 f of x dx, right? So let's take a look at this one. We have the integral from negative 2 to 9, right? So I'm going to write negative 2 to 9. I'm going to make this a plus, and then that integral would become 5 to negative 2. Right? You swap those sides. The integral from 7 to 7, remember, is just 0, right? Because if we have no change in our x, there's no change at all. Plus, let's make this the integral from 4 to 5, right? So it looks like with these negative 2's, we can cancel those and just make this the integral from 5 to 9, right? And then plus the integral from 4 to 5, right? And so these 5's would just make this an integral from 4 to 9 of, we can then write f of x dx, right? So let's take a look at some definite integrals, right? So what's the integral from 0 to pi of sine of x dx? Well, what's the integral of sine of x? It's a negative cosine of x, right? And we're going to evaluate that from 0 to pi. That's how you're going to write it. Okay, so two ways we can solve this. If we have a negative cosine of x, we can write this as negative cosine of pi minus cosine of 0, right? You can also write this as positive, and then you would flip the bounds. So cosine of 0 minus cosine of pi. Okay, either one works. Okay, and we can show that by saying, okay, so here we'd get negative 1 minus 1, which is negative times negative 2, which is positive 2. And here we would get positive, we would get a 1 minus negative 1, which would give us positive 2, right? So we would get 2 as well. Right, so then if we look the integral from 0 to pi of cosine of x, that's just going to be sine of x evaluated from 0 to pi. So we're just going to have sine of pi minus sine of 0. Right, so if we take a look at that, that's going to give us 0 minus 0. So our answer here is just going to be 0. Okay, so the integral can still be 0. Okay, it can still be 0 if we have the integral, right? So we have to make sure that we're being careful. And again, why actually is that? Well, if we draw the graph of cosine of x from 0 to pi, it's going to look like this, right? And so this area, let's just call it positive area, that's going to equal this area of negative area, okay? And those are going to cancel then, so we would have 0, right? So let's take a look at this, but with u substitution, right? So here, let's say that u equals x squared plus 1. And now what you need to do is you need to change the bounds in terms of u. So what you do is you are going to plug in the values for x, right? So if you plug in 0 here, we're going to get x squared plus 1, where x is 0, right? So it would be 1. Then here we'd have the integral for 3, right? So 3 squared plus 1 is 9 plus 1, so 10, right? So let's keep that in our minds, right? And so our du is going to equal 2x dx. So that's great. This will just cancel and become du, right? So we're going to have 1 over the square root of u, and that's going to be integrated from 1 to 10. Now you can integrate it like we did in those last questions, and then plug back in your x squared plus 1. But here we don't have to do that. Now we can just leave it as u and then just evaluate that integral. So here we would have 1 over square root of u du, right? So we're going to have the integral from negative 1 to 10 of u to the negative 1/2 du. So we'd get u to the 1/2 times 2 from 1 to 10, right? So it's going to be 2 root 10 minus root 1. So it's just going to be 2 times root 10 minus 1, right? So let's take a look at a few more. Here we would have 3x squared times e to the x cubed minus 1. So I'm going to say that u is going to equal x cubed minus 1. And then it looks like du is going to equal 3x squared dx, right? So let's do this one where we actually don't find new bounds for u and we plug it in. So this is going to be the integral from, let's make sure we write this as x equals 1 to 2, because then we won't forget to plug it back in. It looks like it's just going to be e to the u du, right? So that's just going to be e to the u, evaluated from x equals 1 to 2, right? So we then need to plug back in our u. So it's going to be e to the x cubed minus 1, evaluated from 1 to 2. So it's going to be e to the 8 minus 1 minus e to the 1 minus 1. So it's going to be e to the 7 minus e to the 0, which is just 1, right? Okay, so let's now talk about the second fundamental theorem of calculus. Okay, so if we have the derivative of the integral from 0 to x of, let's just say, f of t dt, this is just going to equal f of x. Okay, so basically what we can do is if we differentiate an integral, and the bounds are anything, this doesn't just have to be 0, it could be a as well, any value, we can then just plug in an x. So here, what would g prime of x be? It would literally just be g prime of x. You're going to write this exact thing, but just plug in an x. So the square root of x to the 4th, and it should be the 5th root of x to the 4th minus 2x. Okay. Now, if we take a look at this one, what's the derivative? Well, here we actually have to differentiate these two. And then for this one, well, what's the derivative of an integral, right? So d over dx of an integral, f of x, they cancel each other out. It just equals f of x. Okay, so here we would have, what's the derivative of cosine squared of x? We're going to have to use a chain rule here. It'd be 2 cosine of x times negative sine of x. Okay, and then we're going to have minus 3x squared. Then it's just going to be plus ln of x, right? Then we have the derivative d over dx of the integral from 3 to x squared. So now we need to be careful. So what we need to actually do is technically d over dx of the integral from a to u. So now we're going to u of f of t. That's going to equal f of u times u prime. So that's basically the chain rule, okay? So here, this would equal e to the x squared, but then you have to multiply that by the derivative of this, so times 2x. So that's just going to be 2x e to the x squared, right? And then finally, we have find h prime of x if integral 0 to x squared of square root of 1 plus r cubed. So what we're going to do here is we're just going to plug in the x squared, so it's going to be 1 plus x to the 6th, right? And then we have to multiply it by that derivative of x squared, so times 2x, right? So it's going to be 2x square root of 1 plus x to the 6th. So that's going to be it for our lecture on Unit 6 of AP Calculus AB. Make sure that if you found this video helpful, you subscribe to the channel and like the video. And on top of that, if there's any topics you're still confused about in this unit, please comment down below so we can help clear anything up. Now, Make sure that you stay tuned throughout the month so you can see our unit review guides as well as multiple choice and FRQ practice that we will be releasing throughout the month to help you prepare for your AP exam. Thank you for watching, and we'll see you in the next one.